To determine the optimal lag length in an ARDL model, some software packages can provide us with a table like this one. So we can just compare the AIC and SC at different steps, then choose the one with the smallest value. What I'm going to do next is to demonstrate how to obtain the set of output in Stata, but it's rather in a manual way. Just want to show you how exactly those statistics are calculated. So it's kind of opening the black box. Now let's go back to Stata. Here we have the data ready, and we can estimate a ARDL model. Now you may notice that inflation rate is the dependent variable. I include the one period lagged variable of the dependent variable inflation, and the current term of the changes of unemployment rate. So that's an ARDL10 model. Quietly over here is a command to suppress regression output. So you will not see the output. This is quite regress because we don't need to see it. We know the result already. That's from the PowerPoint slide. What we want to do now is to perform an LM test to check whether that model can meet the no autocorrelation assumption for OLS. So we request the LM test, and we would like to see the test up to lag 5. So that's the result. And that's almost identical. That's actually identical with the output on my PowerPoint slide 37. So it's indicated there's a high order of autocorrelation issue in this regression model. We need to find out optimal lag length for both P and Q. In other words, how many lag terms of those independent variables and the dependent variable should we include in the regression model? In the document that posted online, the Stata file, you will find this set of command here. I copy and paste them in this window. You can do the same. So it is a PDF file. You can easily copy and paste over here. Let me explain. For values is a Stata command. It helps you to loop those values, the value of P and Q from, for example, you loop the value from 0 to 1 for Q, and you loop the value from 1 to 6 for P. So it's a very efficient way to run a large number of identical regression, but just with some slight changes in those parameters value. So what did we do repetitively within this these two loops? First, we run a regression model, okay, and we use quietly to suppress the output. Otherwise, you will have a lot of output, and this window is going to be really busy. So we suppress it. Just run a regression model and keep the result in the memory. That's it. So INF is the dependent variable, and we use the lag terms of INF, and we use P to control how many lag terms we have in each step. So that's from 1 to 6. Then INF, this is the lag term of the difference in unemployment rate, so DU. So that's from 0 to Q. So that's what we're going to do. And we use this if date is greater than TQ. That's basically, it's the third quarter of 1988. We use this because we want to have exactly the same number of observations in those steps. You will see the effect later. This is because by using different lag terms, lag length, we're going to have a different number of observations. So if number of observations are not the same, it will affect the calculation of SIC and BC. So the comparison might not be appropriate. As a result, if we start with the smallest sample size, which is when lag length equals to 6, that will help us to have the result that are directly comparable. So that's the purpose of using that if clause over there. Then next one is just to show the, to tell the software for every single step after running this regression model, do not show the result, but only display this one. Okay, that's the value of P and Q in this particular step. Then we calculate AIC and SC directly by using the regress the residual sum square, number of observations, and the rank of the variance covariance matrix. Then we also store the number of observations into a variable called OBS. Then we use list to display those 3 variables on the screen. So what's the effect? If we press enter, that gives you the AIC, SC, and the number of observations for each combination of P and Q. You may notice that Q goes from 0 to 1 and P goes from 1 to 6. And the number of observations are the same, this 85. That's the smallest observation that you can have. You may wonder, okay, what if I do not include that if? If I remove this if, for the shorter lag length, you will have more observations. So you may bear in mind that, okay, if we have that if, the number of observations is 85 for all those regressions. But if I remove that if, you may notice, okay, if P equals 1, that's 90, P equals 2, that's 89, P equals 3, that's 88. And the smallest number of observation is 85 when P equals 6, because that's when you lose the most number of observations. From this set of output, we can tell that when P equals 4 and Q equals 0, it gives us the smallest AIC and SC. So this is without the constraint on variable sample size. But if we go up to the output over there, that will give us the same result as well. So if we compare the value for AIC, at this step, it has the smallest value, and same thing's true for SC as well. So our next step is to specify this model and then check whether it can pass the LM test. So the command that we need to use is this one. Let me just copy and paste from the document. So the dependent variable will be INF lagged by 0. Then the lagged 1 to 4 dependent variable will be included in the regression model. And only the current term of DU will be included. So run this regression model. That's our output. And then we will request the requested test, LM test, then find out whether it can pass the LM test. So LM test can be requested by using this command. We used that before. Just copy and paste here. And you may notice that the null hypothesis is not rejected at any lags that we investigated. And we checked up to lag 5. That's pretty safe. So after we find the appropriate lag length for both P and Q, the ARDL40 model passed the autocorrelation test. It doesn't violate the OM's assumption. Our next example used a different data set that's Occam's rule. So we need to clear the memory and reopen that file. So what we can do is to go back to the document that posted online. The command lines are there, copy and paste them into the command window. So we use a different data set as Occam, and we clear all the variables, then generates the time variable. So you may notice your workplace changed already. The variables names are changed. Then we estimate a ARDL02 model as indicated in the PowerPoint. So this is the regression model. Then we check whether it can pass the LM test. We check up to lag 5. Unfortunately, according to the output, you may notice that all the values in this column, the p-value of the test, is smaller than 1%, which means the null hypothesis of no serial correlation is rejected. That's a clear indication of autocorrelation. Now we would like to see, okay, if we increase the lag length of P and or Q, can we find a model that can eventually pass this LM test? So what we can do is to use the procedure that we introduced before on previous slide. So that's the command that you can copy and paste from my document, okay? And press enter. That gives us the output that is summarized in my PowerPoint slide. So it gives us the AIC, SC, and the number of observations for each step. And if we compare the value of AIC this gives us, let me use this annotation. So this step gives us the smallest AIC, and if we compare SC, the conclusion is the same. So that's the optimal leg length identified by our program. So let's go back to the command window, then estimate the regression model accordingly. So we're going to use an ARDL11 model. So this is the specification. Estimate it first. Then we use the same command line to request the LM test for this model. So remember, every time when you submit this command line, it performs an LM test on the regression analysis you have just completed. So if you run something else in between, that may cause some confusion. To be on the safe side, whenever you need to request LM test, make sure you request it straightly, just right after estimate regression model. Okay, so this is the LM test for this ARDL11 model, and you may notice that the p-value here are all greater than 5% or even 10%, any conventional significance level, which means the null hypothesis of no serial correlation is not rejected at a 5% level, which means this model passed an LM test by using the one-period lag term of the dependent and independent variable. It met the no autocorrelation assumption behind OLS. The next example is an AR model only, and also an example of the cases when AIC and SC do not agree. Okay, so we focus on one variable only. It's an AR model, so we have only one variable, and that's G, or the real GDP growth rate. And we check up to like to 5, whether AR 1, 2, 3, 4, 5 is the best model. Okay, so press enter, and we have the output over there. And if we look at AIC, the smallest value actually is when P equals 4. But if we check SC, the smallest value is here. So when SC equals 2. When you have AIC and SC disagree with each other, the convention is to choose the one according to SC, because SC is usually smaller than AIC. And the performance of those two models usually will not be significantly different. So on the whole, it's a nice trade-off. We want to have a model that's kind of parsimonious with the smallest number of lag term as much as possible. So on that note, we will estimate this AR2 model. That gives us the result over there. And the AR2 model, let's check whether it can pass the LM test. So once again, we submit this result, and to our delight, the p-values in this column are all smaller or greater than 5%, which means we can conclude the AR2 model can meet the OL's assumption. It's a good model that is free of autocorrelation.